All right, good day everyone, and welcome to another episode. Today we have a question on trigonometry that talks about using the MOIVRE'S theorem with n equals 4. So we should prove that cos 4 theta equals 8 cos to the power of 4 theta minus 8 cos squared theta plus 1. And hence, we should show that cos pi over 8 equals 2 plus square root of 2 over 4 to the power of 1 over 2. So now, the first thing we want to do is to write out what the de Moivre's theorem is actually saying. All right. So the de Moivre's theorem is actually saying if I have cos theta plus I sine theta. So the I is actually coming from a concept of complex numbers to the power of n. It's actually the same thing as saying cos n theta plus I sine n theta. All right, so I'll call this the first equation. So this is what the de Moivre's theorem is saying, that if I have a cos theta plus I sine theta to the power of n, it becomes a cos n theta plus I sine n theta. It's more like the n comes down. So if I impute my n to be 4 here, we'll have something like this. We'll have cos theta plus I sine theta to the power of 4 would actually be equal to cos 4 theta plus I sine 4 theta. Right. So once we do this, the next thing we'll probably want to do is to exchange the left-hand side and the right-hand side, right? So I'm just going to switch their position. So I'm going to have cos 4 theta plus I sine 4 theta equals cos theta plus I sine theta to the power of 4. So the next thing I want to do is, like I said, this is the left-hand side of the equation, and this side is the right-hand side of the equation. So what I'll do now is to expand the right-hand side of this equation. So I'm going to expand it. And when I do the expansion of the right-hand side, I'm going to have a cos 4 theta plus I sine 4 theta equals to a cos theta to the power of 4 plus a 4 into bracket cos theta to the power of 3 in bracket I sine theta plus 6 into bracket cos theta to the power of 2 I sine theta to the power of 2 plus 4 into bracket cos theta and I sine theta to the power of 3 plus I sine theta to the power of 4. So what I've done successfully is just have, in the expansion of the right hand side here, that's expanding this to the power of 4, I just simply applied the binomial expansion principle using the Pascal's triangle, or more like the Pascal's theorem. So that's exactly what I applied in that right hand side, right? So you could go through the binomial expansion using the Pascal's theorem and the Pascal's triangle to better understand exactly what was done in this expansion, right? So if I continue what I'm doing, I'm going to have a cos 4 theta plus I sine 4 theta to be equal to cos to the power of 4 theta plus 4 cos cube theta, then I sine theta plus 6 cos squared theta, I squared sine squared theta. So I'm only just expanding the brackets there. Then plus 4 cos theta I cube sine cube theta plus I to the power of 4 sine 4 theta, or sine to the power of 4 theta. so that at the end of the day, I'm going to have something of this nature from my knowledge of complex numbers, right? We could actually recall that for complex number, I squared is actually -1, right? So if I'm having a I cube, I can write it as I squared times I, and that will give me a -1 because I squared is -1 times I, so that will be minus I. So it means that I cube is actually minus I. And I could also say that I to the power of 4 is going to be at I squared times a I squared, and that will be a -1 times -1, and that's 1. So it means that I to the power of 4 is 1, I to the power of 3 is a minus I squared is -1. So anywhere I see I'll probably want to fix this in. So I'm going to have a cos 4θ plus 4I cos cube theta sine theta, this one here, then plus I squared here is going to become -1. So I think this should probably be -6 cos squared theta sine squared theta. Then I cube is actually minus I. So I get a minus 4I cos theta cos theta sine cube theta. I to the power of 4 becomes 1. So this one just becomes a plus sine 4θ. So at the end of the day, I'm going to collect the i's together and the one without I together. So I'm going to have a cos 4θ plus I sine 4θ to be equal to cos 4θ minus 6 cos squared theta sine squared theta, then I think plus sine 4θ, right? Then the continuation would have a plus 4 cos cube theta sine theta, then minus 4 cos theta sine cube theta. But I'm going to bracket this with an I. Right. So what I've done so far is that I've tried to bring the terms that has the I together. And that's what you have here. And I brought the ones without the I's together. And that's what you have here. So that at the end of the day now, if I compare the left-hand side with the right-hand side, so to speak, this is what I'm going to have. Comparing the left-hand side with the right-hand side, I'm going to have something like this. That my cos 4θ on the left-hand side, which doesn't have an I, will be equal to the terms that doesn't have an I on the other side. And that will be a cos to the power of 4θ minus 6 cos squared theta sine squared theta plus sine to the power of 4θ. And my sine 4θ, the one with I on this side, will just be 4 cos cube theta sine theta minus 4 cos theta sine cube theta. Right. So, but because I'm interested in, because the question asked me to prove cos 4θ, which is what I'm going to do, I'm going to eliminate this. I'm not interested in this. I'm interested in this. So I'm going to rewrite this again now and continue from there in order to prove exactly what I have. So from here now, I'll just pick it up and I'm going to take this cos 4θ here out and continue with the solving. So I'm going to have a cos 4θ equals cos 4θ minus 6 sine squared theta cos squared theta plus sine 4θ. Right. So now, because I'm trying to prove what I have at the top, if I go back up, I'm trying to prove this particular expression, and you observe that it all has a cos in it. So because I'm trying to prove that, I'm going to make sure that I don't have a sign in any of my equation for cos4θ. So because I don't want any sign, right, I'm going to employ some trigonometrical identities. But before I do that, I think it's logical for me to write 6 sine squared theta cos squared theta, and write this sine 4θ as sine squared theta all squared. So that 2 times 2 here gives me the back the 4 that I have here. So I've not really changed anything. So I'm going to use the identity that says that from the trigonometrical identity that says sine squared theta plus cos squared theta is actually 1. So making sine squared theta the subject, I'll have sine squared theta equals 1 minus cos squared theta. So I'm going to fix in 1 minus cos squared theta to replace anywhere I see sine squared theta in this equation. So I'm going to be having a cos 4θ equals cos to the power of 4θ minus 6 into bracket 1 minus cos squared theta. So sine squared theta has been replaced. And I have under cos squared theta plus this one becomes 1 minus cos squared theta all squared. Right. At the end of the day, I'm going to have a cos 4θ minus expanding this minus 6 times 1, or 6 times 1 will give me 6 minus 6 cos squared theta plus on this side I'm going to have a 1 minus cos squared theta and another 1 minus cos squared theta. That's into 2. Right. So at the end of the day, I'm going to have something of this nature. Right. If I go on, I'm going to have a cos 4 to the power of theta minus expanding this. I'm going to get, or let me, there's a cos squared theta here. So let me bring it in. I have a minus to be 6 cos squared theta minus 6 cos to the power of 4θ plus expanding this one after the other will give me a 1 minus cos squared theta minus cos squared theta plus cos to the power of 4θ. So I'm going to have cos to the power of 4θ. Using the minus to open a bracket with minus 6 cos squared theta plus 6 cos to the power of 4θ plus here I'm going to have a 1 minus 2 cos squared theta plus cos to the power of 4θ. So basically I just expanded this by saying 1 times 1 is 1. 1 times minus cos squared theta is minus cos squared theta. Minus cos squared theta times 1 gave me this. And minus times minus is a plus. Then cos squared theta and cos squared theta gave me cos to the power of 4θ. So when I look at this now, I can see that cos to the power of 4θ plus 6 cos to the power of 4θ plus cos to the power of 4θ are like terms. So 1 plus 6 plus 1 will give me an 8 cos to the power of 4θ. Then minus 6 cos squared theta and minus 2 cos squared theta. Minus 6 minus 2 gives me a minus 8 cos squared theta, then plus 1. So that's how cos 4θ was proved to be cos to the power of 4θ minus 8 cos squared theta plus 1. And that's exactly what we're asked to prove if I go back to the top here. So that has been finally proved. Right. So with that in mind, we're confident that that has been successfully proved. Right. So that's exactly what you have. And so I'm going to leave us now. And in the next chapter, we're going to take the next question. Right, so that we can actually go through this and digest this, because we still have one more question to solve here that says we go show that cos pi over 8 equals that sort of expression you have on the right hand side. So we're going to do that in the next video, but for now let's understand the De Moivre's theorem and how I was able to use that in my expansion, and understanding how complex numbers too work. Very important. So all of this ascertain the understanding that you get from this concept. So for now, I'm going to leave you with this to understand better. If you have any issues with anything in the video that you don't understand, you probably just communicate to us through our email, or you need any help on any topic, just let us know in the comment section, or just send something to our email there as ziglaginstitute@gmail.com. I will definitely respond to whatever help you need. Thank you for now. God bless you.